March, what is it, March 12th? Yeah, March 12th. I'm saying this obvious stuff because I need to take a screen recording of what we're up to. And so for that reason, we need to, Blue Jeans has an upper limit of 25. This is, I believe it's probably enforced automatically by SFU. If there's more than 25 people, SFU has to pay $1 per minute per user for the extra people. So, yeah. So anyway, what I'm going to do is I'm going to screen capture this thing. And so it's going to take a little bit of time and fiddling around, and it'll probably be messy, such is life. So anyway, let's get started. And I'm going to now, yeah, get started. So today's topic is temporal visualization. And what we're on about today is the visualization of temporal data, time sequence data, and other things that are related to time as a primary domain of interest. So that's today's topic. Many of the previous visualizations may have had no time at all, or they may have had time as an independent variable upon which other things are controlled, at least a little. So anyway, we're going to talk about that stuff. So temporal data is simply data that represents a state in time. That's the most stripped down idea of what temporal data is about. And temporal data analysis commonly is about change over time. And some of the time you want to do, I'm going to say time too much in these sentences. Some of the time what you want to do is you want to just see what has happened over the course of time for some phenomena of interest. And sometimes you want to see cause and effect or some other kinds of relationships in which one thing causes another or flows to another. We're going to talk about those topics. So what do we mean by time? So in the little table we're seeing here, we see on the left in slide 3, events, intervals, ranges, process, state, and transition. That is to say, one of the things that you want to see in time is things that have happened during the course of the week or the month or whatever it is. Another thing that's very important is intervals that, and you could strip that down to a representation of an event that starts at some time point and ends some point later. And so anyway, that's a time sequence that is often of interest. Hold on one second. Anyway, third is, here is ranges, that is to say ranges of time. You also commonly want to see process state. Something is, so you have a collection of entities that are doing separate things over time, and you want to see them transition from, say, loading the truck to the truck driving around and delivering things like that. And often it's very important to see the transitions. You know that the truck is going to get loaded, and what you're really interested in is when that loading happens and when it arrives at that destination, and if there's any delays happening at that destination, because let's say you're looking at transport and you care about the endpoints, not about the fact that there's traffic and the driver is driving around town. One of the common uses in the stuff we see every day in the newspapers and online is trends. That is to say, you have some kind of figure of merit, say stock prices or whatever it is, and you can see the number increasing or decreasing over time, day after day, week after week. And of course, changes in the actual value, trends, is a sort of an overall description of what is happening over that time period. It's a similar idea with timelines. Another thing that we'll talk about later in the lecture is often, our regular experience of time is that it's cyclical. There's daytime and nighttime, and things happen according to the time of day. We eat lunch nominally at 1 o'clock, stuff like that. And those kind of cycles are often interesting because it might have some effect on some other phenomena of interest, things caused by eating lunch or things like that, things that happen at bedtime or at wake-up time, stuff like that. So another closely related thing that we're interested in is geotemporal, that is to say, things with times attached to them that are happening over space. Going back to the driving a truck and delivering example I was speaking of briefly, you want to sometimes care, instead of what's happening at the delivery points or at the pickup points, you care about what's going on in between, and maybe a route is being blocked regularly for some reason. Closely related to time stuff is sequence and process flows. These often have a time involvement directly, but it might be the case that the notion of temporal visualization, you can use that as a metaphor for other kinds of visualization for things that have a linear arrangement of some kind, and I'll show an example later on. So one of the things that you care about is trends or continuous change over time. And here's a classic. This is a pair of timelines. In this case, it's a recap of the 2016 federal election for the U.S. president, and you can see the change over time, and the shape of the trend is the critical information point that you're looking at. So here you could see that the pundits were saying up until about midnight that earlier on in the in election night that Trump's chances of winning were down below 20%, and then everybody got surprised when lots and lots of folks were voting for him and voting, I guess, against Hillary Clinton. And so this is the visualization here is a classic timeline visualization. Here the units are very short. Each of these tick marks represents an hour at Eastern time, and that shape is the thing that you care about. Here's another visualization. This is another temporal visualization in which instead of hours being depicted, what's being represented here is years. And so this is a visualization of cricketers. I know, pretty thrilling. At English Test matches, that's championship matches of the game of cricket, and naming the individual players who are swinging the bat on the cricket pitch, and indicating the number of runs that they have scored essentially throughout their entire career. And what they're saying here is this guy Alistair Cook is the best batsman ever for whatever reason. I don't follow cricket, but a lot of the rest of the very strong batsmen over the preceding, say, 50 years, had were very strong, but kind of had an upper limit of their, for whatever reason, probably just due to career longevity. But perhaps it's Cook had lasted a little longer his career lasted longer, so that's why his curve exceeds the others. These timeline visualizations go back a long way. There is a long history of doing timeline visualizations. So this one is from the 1790s. It's by a guy named William Playfair. He was an economist, and what he's doing here is plotting the total pound value, English currency value of imports, and that's the orange line here, and exports, which is the reddish-purplish line. And what he's doing is plotting the interval in between, which is the balance of trade expressed in monetary quantities. And what he's showing here is that from 1700 to about 1750, England was in a trade deficit situation, and then starting around 1755 and up to 1780, there was a significant balance of trade in favor of England. That is to say, greater number of imports from exports, greater value of exports compared to imports. So this is, a classic timeline visualization. On the right, you can see the kind of scale that both of these things are on, which is these figures you see, 10 to 190 times 10,000 pounds. Here's another one of these visualizations. This is about showing baby names in England and Wales, and the trend for, sometimes names become popular and then they fade in popularity, and we see a bunch of graphs of that, and I'll have another visualization of that kind of idea coming up. And what we're showing here is in the crowd of baby names, which is the collection of all names in these subsets plotted on top over time, going from 1905 to 2015. And, we all sort of kid around about, somebody being named Ethel because, that's not a popular name anymore. Here's another variation of that. This is using US data. And if things work the way I hope, I will be able to navigate to that screen. Hopefully, up there. This is this thing called Baby Names Voyager. This takes U.S. Census data and plots names of boys and girls, and just uses the census data as an input to plot the popularity of first names of various kinds. And so I will type the letter I, and what it does is it shows you a transition from all the names to all the names now beginning with I, both boys and girls. And we can see that Ida was popular from the 1880s through the 1940s. And, it's a very, very uncommon name these days. You do see a few. There's a slight, I don't know if you can see it in your display, but there's a slight 900, it's not Ignacio actually, but there's a slight number of people who are named Ida these days, probably by hipsters. Anyway, and the other thing that's kind of interesting about this particular one is that names start with the letter I, sort of dropped off in popularity from the 1930s through the 1990s. So anyway, so each of these things is showing a trend in in something. In this one, what we're doing is stacking up all of the individual quantities. So it's a stacked line chart in essence, and the most popular, because there's a lot of people named named say Mary in this case, shown on the image on the left. Sorry, let me make that larger. That means that you have the opportunity to be able to put a label in there because there's enough space to put a label. So, so one of the things that this thing's doing is showing the name if there's enough space to show it in the largest amount of vertical and horizontal space, wherever there's enough space to do it. Here, there's names shown. There's a name shown here. There's a modest amount of space. It's a little bit hard to read in this particular screen capture, but it's the same basic idea. So what we've shown is a bunch of examples of timelines, right? And what I would like to do now, just hold on one second. I'm going to pause sharing for a second. And okay, I'm back. What we're doing is plotting one or more quantitative values that are nominally continuous. The names don't, the quantity of names shown in this plot aren't actually continuous. It's not the case that in every divisible amount of time there is always a name, somebody being named, although, people are born regularly. But we can treat it as continuous data and draw something approaching a continuous line chart, although you can see the segmentation of the line segments here. Let me make this full size again. Whereas every 10 years the census is done and they're recording the names according to the census year. But we're just essentially treating this as continuous data in this case. Here we're doing something a little bit different. We're plotting values both in X, quantitative values both in X and in Y. And what we're doing is, what's going on in this plot is the horizontal dimension is sequence according to year. And so this is plots of Olympic Games and participants. The number of participants is essentially the entire area of each individual vertical slice here. And there's a division between women participants in orange and male participants in this cyan kind of greenish blue. So the width is the total participants, and at each Olympic Games, and the vertical proportion shows the number of participants, women versus men. And as you can see, there's a continuing increase of the number of women as a proportion of the total moving forward, and also a continuing growth in the quantity of participants over time. So there we're using two dimensions by relaxing the usual kind of assumption that time is an equally spaced scale on the horizontal axis. Here it isn't. We're essentially plotting subsequent items one after the other. The other thing that you can do with temporal data is if you have, one of the things that you're often interested in with temporal data is what might happen in the future, what are the ranges that you might expect. The domain of analysis is commonly statistics, examining prior history, perhaps some simulation is going into this. And the reason why I mentioned simulation is I do simulations to getting a handle on future demand for CAT courses, for example. In any case, this is a plot of a quantitative value, and that's inflation over time. And on the right is a percentage plot. So this is 5% inflation, 4% inflation, et cetera, et cetera. And the horizontal line is essentially likely to be the target inflation rate, because this is a inflation report by Bank of England. It's essentially a planning report, and the central banks typically have a targeted inflation rate that they're trying to hit. And generally it's about 2% inflation that they want. So there's the target there, and what Bank of England is doing is showing prior rates of inflation and possible future rates of inflation with using the color to indicate the likelihood of inflation according to the plans that they've put in place, according to the policies that they've put in place. And, they've simulated and so on and so forth to get a sense of what the policy might hold. Now, this kind of plot assumes things are going along as normal, and, right now we're not in normal times, as I'm sure you're aware. One of the things that can cause a problem, however, is if you have large amounts of data, large amounts of temporal data, you could, if you plotted it all together, you could end up with kind of a mess of overplotted line segments in this case, or overplotted marks indicating the numerous data items that you're interested in. And occasionally you are able to restrict the amount of stuff that you're plotting per unit area by breaking up the data set into smaller pieces, in this case, small multiples of data. So in this thing, again, this is a temporal plot. There's just 2 years being plotted here, 2004 and 2014, but it's being plotted 6 times. And one plot is for the United States as a whole, and the other 5 are, roughly alphabetically, 5 states in the USA, Alabama, Alaska, Colorado, Connecticut, and Delaware. And what's being plotted here is the proportion of electricity that's generated by whatever power source. I'm presuming this is taking into account only local generation, not power imported or exported to another state. And so one of the things that I imagine you're aware of if you follow environmental news is there's been a significant decrease in the amount of power generation done by coal-fired power plants, mainly because, first off, for environmental concerns, both in terms of air pollution as well as concerns for global warming, and coal-fired power plants are expensive to run, and there are other fuels or other means of generating electricity that are becoming more and more competitive, and this set of graphs kind of bears that out. The trend that has happened over the preceding 10 years, well, actually 15 years, considering it's now 2020. So there's been a drop in 10 percentage points across the board in the USA in the amount of electricity generated by coal, and an equal increase, so to speak, in the percentage generated by natural gas. And commonly what's going on is each of these plants has their fuel converted from coal to natural gas. Not all states have the same profile. Delaware has this very large change, and it's likely, because Delaware is a very small state, that this is a single power plant that changed its fuel mix over here on the right, and one power plant, one or two power plants, change from coal to natural gas, and that's why you see this big change. Sometimes using time as the primary dimension of temporal visualization is not necessarily the most interesting things. One of the things that you're often interested in doing is plotting change over time, and change over a number of different data points. And so here is this is intended to be something like 450 odd U.S. House of Representatives in the U.S. Congress, how changes occurred in voting patterns and how the margin of the win shifted from the years 2014 to the year 2018. They're using this kind of the standard USA News color code, and that is blue stands for the Democratic Party and red stands for the Republican Party. And so what they're plotting here is each arrow represents an individual race for the U.S. Congress. The tail of the arrow indicates the vote, the values from 2014, and the head of the arrow indicates the value for 2018. And so there's roughly about 450 arrows here. And you can see that the overall sort of trend here is that there's a shift somewhat towards more democratic voting over that time. And there's also an interactive filter on this thing where you can select only those that have shifted left, shifted right, and also where turnout has increased or decreased. So some of these races, there's been a very significant increase in turnout for many of the Republican wins. You can see that, but by and large, you can see overall that the trend here is towards in this electoral comparison, a shift towards the Democratic Party in between those two races. And those are midterm years, in case you follow U.S. politics. Here's another visualization in which time is being plotted here, but the way in which time is being plotted is that each of these individual, essentially leaf-shaped ellipses, is indicating a change in whether spring is starting earlier or later. And the thing being measured here is the appearance of the first leaf on trees, presumably some well-defined species of trees that's being looked at by horticulturalists between the years 1951 to 60 and the years 2016 to 2006 to 2015. And so, interestingly enough, you can see a very significant change in the U.S. Midwest, more than spring seeming to occur a little more than 7 days earlier in the year over the last preceding 50 years. Also, in our neck of the woods, spring occurring a little earlier. But that's interestingly not universally true. There's in the U.S. South, there's spring seems to be starting more than 7 days later as a general trend. So it's interesting that that's not uniformly distributed. There's also spring occurring earlier in Florida as well. So here what's being, the thing that's of interest is the geographic distribution of the onset of spring and how that varies from place to place in the continental USA. And the time, instead of being a primary dimension for plotting, it's it's discretized into 6 steps: 1 to 3 days, 4 to 7 days, and more than 7 days as 3 separate marks, each readily distinguishable from each other, and earlier being distinguishable from later by simply by the use of color. So here is, on this one, you can see this is another temporal plot. This is plot of high temperatures. This idea here is to take snapshots of years, year by year. This is January, June, and September, showing the shift in expected temperatures in those forecast years. And essentially what we're doing here is using time as a dimension to indicate anticipated climate change in the future where we're discretizing years. Okay. So one of the things that you typically see for all these plots, but not for all, for many of these plots rather, is timeline, a linear axis. But when what we have been showing there is visualizations of some process that has occurred over time, and somebody has their hold on one second. Yeah, just for a second, someone had their mic open. So when you're joining, make sure to turn your microphone on. Okay. Just one second. Okay. Getting back to business here. Okay. So anyway, typically time's plotted on a linear axis, but although in the later examples we're taking discrete allocations of time in displays where we're distributing separate time values across the geometric layout of the visualization. Another way that time is typically used is in planning and plotting of activities, and you commonly see that in Gantt charts and histograms and bar charts. Let me make the thing full size. So here is another classic timeline display. This is a visualization of release date of popular music albums. And here we're showing, instead of plotting individual things as if they were trends, what we're doing is in some sense plotting events as across time, starting from 1972 and ending in 1992. Right. We'll move to the next slide. Here's another mode of showing timelines. The thing that's intending to be gotten across here is the longevity of individual leaders of countries across Europe. And here on the bottom we see the timeline starting from 1990 going to 2000, essentially 2018. And instead of plotting a number of charts, a number of line segments indicating the longevity of a person in charge, allocated horizontally, what's going on in this thing is that we're plotting individual people as a diagonal line from their starting point of when they were in office and the end point indicated by the dot and possibly a label. So here we see Silvio Berlusconi being plotted here. And this is the timeline for Angela Merkel, and she's she's been at that job a long time, but she's not the longest person on the job. There's Erdogan and Putin, who are also been around a long time. Geez, I wonder why. So here, what's going on is we're using the time when they started, these individuals started on the job, as a means of also distributing the marks along here, so that each individual person can be distinguished from each other. And so this is kind of a clever layout rule where you're able to see all the individuals who are present in the display, and you could presumably interactively query on these things to see some of those folks who hadn't been long in the job. Okay. So one of the things that is commonly a problem, that the previous thing about, let me go back one, that the European, European leaders plot attempts to address is this challenge, going forward one slide to slide 18, of overdrawing, of drawing too much stuff and having all the stuff you're drawing on top of each other all obscure all the other stuff. And it's a standard problem that you have to deal with in timeline plots. So one of the ways of grappling with that is to have a common time dimension shown here. This is essentially a century, 112 odd years of recent history, and the way in which certain words in, I think this is inaugural addresses being shown here, and the way in which there has been a shift in the quantity of certain words in presidential inaugural addresses. So here on the top we see America and American has been reasonably common, but has become a little bit more salient since roughly the 1960s. Freedom as a kind of a political term had, wasn't really mentioned so much or very frequently starting up until about 1930, but from 1940 on, it's starting to become fairly common in inaugural addresses. Whereas democracy does show up here and there, and the world has shown up fairly consistently, perhaps less commonly before World War II than in later years. So what's going on here in this plot is we're just simply plotting a circle according to the quantity of times an individual keyword is mentioned, and what we're doing is using what's going on is that we're using a query to select the words that we're interested in and showing how that word usage has shifted and increased, waxed and waned over time. This is to enable you to do this textual analysis of the kind we sort of talked about on Tuesday, that it enables you to be able to get a good understanding of what's been going on in speeches, but being selective about what we're able to plot. One of the things that will be hard is to see all those words over the entire century and century and a quarter of inaugural speeches, and so you have to essentially subdivide that thing in some way. And here, what's been chosen to do is to subdivide that according to salient words that are interesting. So this is the outcome of an analytical process in which these plots have been generated on the basis of things that the folks who put the plot together thought was interesting. One of the other classic uses of timelines has been for planning, and so one of the standard planning tools is the Gantt chart. We have some examples shown here. You can get Gantt chart planning software. It's also, you can get a plugin into Excel that enables you to do this. Basically the way the Excel one works is you type in cells basically at the beginning and the ending of an event, and it uses a common timeline, which in Excel is essentially a sequence of cells with equal divisions of time, typically. And but in more freeform plotters, that you have a timeline across the top, where now or some time in recent past is on the left, and on the right is essentially the planned completion date of the project. And the purpose of the Gantt chart is to show individual activities that need to go on in the project, possibly who's going to do them and how long it's going to take. And part of the reason to do this plotting is to get a good sense of where there are tasks that can overlap each other and can be done by individual teams or individual people. And I'm sure you guys have used this kind of stuff in your project course. So here, what's of interest is to plot intervals, and also to give, particularly you can see this in some of these other ones, to give the possibility that there might be a start. You have a planned start date and a planned end date, but you might plan for space for things to not work out so well, so you need to plot the amount of time you might leave spare just in case something goes wrong, because something will go wrong. So these things are essentially plotting time directly where the horizontal thing is intended to plot the interval for an activity, and here What's being used, plotted here is essentially the vertical extent is being used to plot the quantity of time, and so here we're using essentially a bar chart type of representation for temporal visualization. So here's another variant on a Gantt chart in which the starting and end points are detailed in the annotations for each of the bars, plus some milestones that need to be met throughout the project. One of the things that often is the case is that outside of the domain of planning, you're often interested in how events have transpired over time, and so this thing is something called trace view, and this is showing both intervals and events that have taken place over time. Here we're at a very small time scale. We're talking on the order of seconds, but this is the interaction of a number of computer processes and things that have communications, presumably, that have happened between processes and where processes are spending their time or are otherwise idle. So that here in process 10, this thing's only active between 13.75 and 14.3 roughly, and then activity goes to process number 9. So this is an indicator of the activity of a number of coordinating processes. If you were interested in finding out how much parallelism was going on inside, if these processes are all part of one sort of application, finding out whether or not there's any parallelism, and there is a little parallelism here. That is to say, two processes able to do things simultaneously if you have a multi-core CPU, but largely this is a sequential process that's being depicted here in this diagram. I think I'll skip this one here. So for diagnostic purposes, another use of timelines is to show the history of things that have happened, and so this is a e-patient's medical life history view. And here what's being shown is two general factors with annotated events of interventions. And so what's happening is that with this patient, they're having some gut problems. Their digestive system isn't working well, and they have some kind of weakness. Their digestive system isn't working well. They're feeling generally sick, and this is a plot of the log that the patient has kept for their feeling of gut upset and weakness as presumably as a result of gut upset, because commonly they interact with each other. So here is a plot of how the digestive system didn't seem to work very well, and there's a couple of interventions here. This one showing antibiotics and another intervention of antibiotics, and that seemed to make the gut problems go away, but then there was another onset plus a more severe type of things. And so there's plotting of this kind of stuff on the timeline. The reason why it can be valuable is to get an assessment of how interventions are affecting the symptoms. And if it's the plotting of the timeline is useful, so you can get a retrospective view of what's going on with the patient's symptoms. So now we'll show an interactive example. I'm hoping this is going to show up for you. So this is a plot of living U.S. presidents. This thing is again showing overlapping timelines, but in this case is not the entire lifetime of an individual, but the onset of somebody becoming president and how long they lived after they resigned from the presidency, or got voted out of office or whatever. So here we have Harding. He was president for 2 years roughly, and then he died in office. And then Calvin Coolidge, presided over the onset of the Great Depression, and then died in. Sorry, I got mixed up there. He was president from 1923 to 29, and then died in 1933. It's Hoover. He lasted a long time after his presidency was over. And so you can see that here I've been really focusing, by the way, when I'm talking about this, is the time in office of these individuals, but what's being plotted above is a coordinated view of the number of people who have been, number of U.S. presidents who have been alive at the time that is being selected by the mouse cursor. So you can see in the PowerPoint slot, hold on, I'm going to pause sharing for a second. You can see in the PowerPoint slot that there we've got 1858 selected, and we can see Martin Van Buren, John Tyler, Millard Fillmore, Franklin Pierce, and James Buchanan were all alive at the time of James Buchanan's presidency. And you can see there's the URL, we can go and interact with that. So that's coordinating temporal interval views along with an aggregation of quantitative value, which is the number of people who are, number of former presidents who were alive at the time. So all of those plots that we've been showing, almost all of them have been showing time as a horizontal axis, with the exceptions of, say, the onset of spring or the shift in partisan voting plots. But one of the other common things that we care about in timeline visualizations is cycles. That is to say, things that happen over the course of a day, things that happen over the course of a week, or over the seasons of the year, that kind of stuff. So another standard mode of visualizing time is to plot events on cycles. And typically, one of the cyclical viewpoints is to lay things out on a circle and to show along the circumference of the circle some kind of attribute that you care about. So in this case, what we care about is the temperature. That's being plotted in a circle where winter is at the top and summer is at the bottom. So this is December here, January, February, March, April. Sorry, this is June here, July, September, August, etc. Sorry, I'm reading these wrong because I'm trying to move my mouse at the proper time. Anyway, so the whole year is represented here. The concentric circles indicate time bands. So this is 20 degrees Celsius, 30, 40, 50, 60, etc. And you can see what the weather overall has been like here in Washington, on the one on the right in Washington, D.C., and in Toronto, where it gets to minus 20 occasionally. Also plotted here are weather events, and at the top is an indicator of the year that's being represented, and then annotations for the hottest summer day, and other things that are going on. So what this thing does give you is a general indication of what the weather is like throughout the year, and these things can also be used generally to plot trends over the year. These timeline plots are, been around for quite a while. Florence Nightingale was interested in she was a nurse during the Crimean War, and one of her great breakthroughs was to introduce sanitary measures, that is to say, washing your hands, something that we're all aware of today with coronavirus, and properly disposing of human waste and all that kind of good stuff. Because in preceding years, prior to the Crimean War, soldiers would end up in hospitals after being wounded and so on and so forth, and would die at great rates due to hospital-acquired infections. And at the time in 1854, there was this theory that some people had thought was possibly a crackpot theory, and that is the germ theory of disease. It's something that we all understand today, but it's the notion that disease is communicable, it's caused by microbes, and that you can do something about it. So what this plot is intended to get across is the uh, the quantity of mortality of soldiers in field hospitals, and this thing is plotting both before and after the onset of uh, sanitary measures. So here we can see the number of deaths. The blue is died in battle, and the non-battle deaths are dying in hospital, essentially. And you can see that the number is increasing very significantly in January 1855, March, and it's decreasing significantly afterwards. So anyway, the idea with this plot is to plot the timeline of when it was that she introduced sanitary measures and a very significant shift from high death rates to low death rates in hospital. Pretty much they started to disappear as soon as she started doing sanitary measures. The advantage with doing that is that she's essentially trying to account for a full year. Here, she's trying to, this is a different plot in which we're trying to plot multiple years, and therefore instead of plotting a single year, we're just laying things out on a spiral. So here, the spiral starts here and just continues to go out. The linear region being plotted here is the same size, and essentially the layout algorithm is allocating a unique chunk of space in a spiral pattern, where unlike, say, a nautilus spiral, the vertical extent, the kind of the width of the strip that's being plotted here remains constant. So it's not a not a spiral of the kind you might see in a nautilus shell, where there's a continuing growth in the size of the spiral. So these circular layouts are also used in other contexts, primarily because it gives you the opportunity to do things in the center of the plotted region. So here is a plot of a genome. Typically, this will be a single strand of DNA inside some organism. And what's being plotted along here are segments of DNA, that each segment corresponding to a gene. And what is plotted in the center is some form of biological activity that connects two genes to each other. So you can see this gene here, whatever it is, has a strong relationship with other genes. Generally speaking, what you might expect is that this gene expresses a protein of some kind that interacts significantly with other parts of the organism. So there's one gene here that puts out a protein that a lot of the rest of the organism uses, and there's a similar one over here that this one uses. And the color is being used on these linking marks to indicate, to distinguish one item from another. So red for this one, and green for this one, and yellow for some of the others. And this thing is from a system called CIRCOS, which is developed by the BC Genome Sciences Center, and it's used commonly in biological circles, pardon the pun, for plotting the interaction of genes with other genes. That is to say, either genes are signaling other genes, or the proteins that they express are interacting with other proteins, which is, of course, some of the things that you're interested in when you're doing biology. I'm including this here essentially for, just to remind you that circular layouts certainly can be used for cycles, but they can also be used for other things, because you can use the interior area to mark linkages. So one of the other things that you can commonly use for timeline visualizations is where you have time and geographic space that you're interested in. And typically, the organizational idea is that you have geography as one of the primary things that you're interested in, and that provides the geometry of the plot. And this plot here is an example of that. It's idealized plot of the City of London. The River Thames doesn't run straight as a die. It actually curves and turns. And this is meant to indicate neighborhoods north of the River Thames and south of the River Thames. And what's going on and what's being plotted in this is something pretty not terribly life-threatening. It's the number of pubs per subdivision of the city of the metropolitan area of the city of London. So here, right there in the city, there's 150 pubs, and the number of pubs has been decreasing a lot, say by 40% from between 2001 to 2016. So maybe the Brits have lost interest in drinking. Who knows? Anyway, so that's an interesting change over time. So anyway, the point of the plot is to show this change and how that change is distributed among various neighborhoods around the city. Oops. Skip this one. So this one is another city-based visualization, and what's being plotted here. Hold on, I'll pause sharing for a moment. Is this is a plot of Brooklyn, New York. And here what's being depicted is the age of the buildings in that neighborhood. And he's using color here in this thing to indicate age ranges from, I think, 25-year chunks, so 75 to 2000, 50 to 75, et cetera, and the blue is before 1825. And you can see there's a significant amount of Brooklyn that is built. The buildings there have been built prior to, since essentially World War II. You know, but there are a few exceptions. There's some older neighborhoods here. Here's a neighborhood where there's a lot of older housing. And what's showing up in the upper right is the year when the building was built. So here, although it is, strictly speaking, a temporal visualization using housing data and from City Hall or something like that, it does give you an approximate idea of the age of the housing stock or the building stock in an individual neighborhood, and it's just using color in these bands to indicate age range. And clearly, you can see from this that most of Brooklyn has been constructed since 1900, with large patches, probably along main avenues and subway lines, built somewhat more recently than that, in the last 25 years or so. Okay, excuse me, I had to do some navigation. So there, it is a temporal visualization. The primary interest there is to display time, but because geography is the primary organizing idea, the temporal aspect of that has to be represented in this very quantized manner. He is the guy who did this, Thomas Reel, has kind of made this fairly standard mistake of using something approximating the rainbow color map here. So it makes the yellows a little bit more salient than they ought to be, and they're just easier to see because a little bit easier to see because they're brighter. And so there's this accidental emphasis on what yellow stands for, which is 1900. Which overemphasizes a particular year range, but at least it gives you the opportunity to interactively visualize and so on and so forth. If you wanted to do some more detailed examination of this thing, you'd probably be interested in supporting other types of queries other than the hovering query of putting your mouse cursor over a building in order to have its year displayed. So next in the sequence of stuff I'm going to talk about is sequences. Here Whereas in a lot of the previous stuff we talked about, time is a primary dimension that you're interested in. We all understand it, and it's used as an independent variable, or perhaps a dependent variable on the basis of where things are located, as you would see in the geographic visualization. Here, what we're doing is taking the concept of time and shifting it to the visualization of sequences of events. And the sequences that could be drawn could be sequences of, in this case, DNA, or sequences of events, as is shown here. And what you're interested in doing is having time as a primary variable, but have another dimension being displayed where time is providing the structure, or ordering is in some way providing the structure for understanding the visualization, but that there's another item of interest that you also want to display, and you want to use a display dimension for that other value. So I skipped ahead. I moved ahead one slide. I'm going to go back to the previous slide in a second. So here, this is pardon me, the career of Michael Phelps. The name of the plot is Michael Phelps versus himself. So he's an Olympic swimmer, as you may be aware. And he'd been swimming for a long time, since he was a kid. And these were his championship, the sequence of championships, swim meets, and his best times over those individual meets. So starting in the year 2000, you can see his time seemed to get better. And here, on the horizontal dotted line, is the time that is required for you to be able to qualify to participate in the 2016 Olympics. And so each line here represents a single race in which he participated in. Slower times are plotted below the line, faster times above. And this thing gives you the scale. So this is 5% slower than the Olympic qualifying time, and above here is 5% faster. So what's being plotted along the vertical plot is indeed time, but it is this particular thing, which is the relationship, the percentage change from the percentage difference from the 2016 Summer Olympic qualifying time. And as you can see, his times at each of the individual swim meets got to be better and better and better up until 2008, and then held steady up until 2012, and then got declined a little bit for 2016, with a lot of annotations indicating, the shift in, what he was doing. So there's times being plotted in two ways here. Horizontally, of course, is the year, and vertically is this percentage. This percentage faster or slower than the qualifying time. And as in 2008 in Beijing, as the little annotation says, Phelps could do no wrong at the Beijing Olympics. He won gold in every event he swam in. So here, what we're doing is using essentially sequencing time as individual year buckets, and then plotting through it on a different time scale, each individual meet according to the time. So you can't read these vertical things in any form of order. It's just simply the quantity of contests that he's been in, and the percentage faster or slower than the qualifying times that he was engaged in. So what I'm going to do is go back a single slide here, and on this one, what this thing is doing, this thing is called Sequence Surveyor. What this thing is doing is putting data in order, but instead of treating the dimension as a continuous value, we're discretizing the dimension in the plot to enable the user of the system to show relationships. So I'm going to show this little subset. Hopefully you can hear it. Hold on. Actually,
sequencer